Hello everyone, welcome to my channel. Today I would like to discuss differential equations of second order. So far we have discussed about differential equations of first order, their types, how we can identify each type and how we can solve these equations. So once again welcome to my new video. Second order differential equations. As we all know, we already discussed about the order and degree of differential equations. So in second order differential equations, we can identify this type by seeing the terms such as d square x by dt square or d square y by dx square and so on. We are only dealing with linear second order differential equations. So the main category we are discussing is that it is linear second order differential equations. For a typical linear differential equation of second order, we can write the equation as d square y by dx square plus p into dy by dx plus q into y is equal to r. Keep in mind that these p, q and r, of these especially p and q should be constants. R can have some values such as r can be a function of x, some exponential function or some trigonometric functions or even some combinations of these functions. But p and q should be constants. Now I would like to introduce you to the new operator called as the differential operator. So for a variable, that is for an independent variable x, we have a dependent variable y. That is why we are representing y as a function of x. Okay. And now we are taking the differential of y with respect to x. That is why our differential equation look like dy by dx or d square y by dx square. These terms are involved in these equations. Now the differential operator d is defined as d is nothing but d by dx if x is the independent variable and d square is the second order differential operator d square by dx square. So simply this equation means that this is nothing but d square by dx square plus 2 into d by dx plus 1. This is not actually a function, this is actually an operator and this is operating on a variable y, or it can further be simplified as d square y by dx square plus 2 into dy by dx plus y is equal to 0. I hope you got the point. Now we can move on to some other properties of second order linear differential equations. Wronskian. So now let me introduce you the new concept called the Wronskian. So if I have a differential equation of second order and let y1 of x and y2 of x be two different solutions of this differential equation. In order to check for the linear independency or linear dependency, we have to define the Wronskian of this particular set. That is, w of y1 comma y2 is defined as nothing but the determinant of y1, y2 and the first order derivatives y1 dash and y2 dash. Depending upon the value of this Wronskian, we can say that the given differential equation, the solutions of the given differential second order differential equation are independent or not. If we are having this Wronskian of the equation equal to 0, if w is equal to 0, then we can say that y1 and y2 are linearly dependent. And if w is not equal to 0, then y1 and y2 are linearly independent. Now we can do a problem. Check whether the following functions are linearly independent or not. So, the functions are given by e raised to x cos x and e raised to x sin x. To check whether these two are linearly independent or not, we have to assign y1 and y2 values for these functions. That is, y1 is equal to e raised to x cos x and y2 is equal to e raised to x sin x. So, Wronskian is given by y1, y2, y1 dash, y2 dash determinant, which is given by e raised to x cos x, e raised to x sin x. What will be the derivative of e raised to x cos x? First function e raised to x into derivative of cos x is minus sin x plus cos x into e raised to x, because derivative of e raised to x is e raised to x itself. Similarly, in this function, it is e raised to x into derivative of sin x is cos x plus sin x into e raised to x. Now, this is actually determinant. Even though we take e raised to x from this row and this row, we will get e raised to 2x into determinant of other functions, but this will not be equal to 0, which clearly show that these two functions are linearly independent. I hope you got this problem. Okay. Now let us move on to the actual solution of second order differential equations. So, we have already discussed about the general form of a linear second order differential equation as d square y by dx square plus p into dy by dx plus q into y equals to r. Suppose this r is a function of x. This is the most general case where p and q are constants or constant coefficients. Now, the general solution of this kind of differential equation will involve two terms. So, the general solution is of this differential equations two terms known as complementary function or CF plus particular integral or PI. So, what is meant by complementary function and what is meant by particular integral? Complementary function is nothing but the solution of the homogeneous part of the differential equation given. What do you mean by the homogeneous part of the differential equation? This is nothing but the RHS equal to 0. So, the homogeneous part of the above differential equation is given by homogeneous part. Homogeneous part of the differential equation is given by d square y by dx square plus p into dy by dx plus q into y is equal to 0. This is the homogeneous part of the given linear second order differential equation. Now, we have to form an auxiliary equation with this homogeneous part. So, the next step is, I am now giving out the steps for solution of complementary function. Okay. The first step is that write the step 1, step 1 is write the homogeneous part of the differential equation. Step 2 is form the auxiliary equation. How we can form the auxiliary equation? First, we have to convert the homogeneous equation into the differential operator form. So, simply we can write this homogeneous equation, that is equation number 1, into a new form regarding the differential operator involved, that is d square y by dx square is nothing but d square plus p into d plus q, the whole operating on y is equal to 0. This is the form of operator form of the above homogeneous equation. Now we have to rearrange it, or we have to substitute instead of differential operator a new variable. We can either use a letter called m, small m, or in some textbook you may find lambda. Here I am using the letter m. So I can rewrite this equation as m square plus p into m plus q, which is equal to 0. Since y is a function and it cannot be equal to 0, and this is an operator part, in order to achieve this result I have to equate this auxiliary equation or auxiliary polynomial to 0. This equation is called as the auxiliary equation for our homogeneous part. Now solve this quadratic equation. We know how to solve this equation, and the solution, the type of result giving from this kind of quadratic equation will give us the way to solve, or will give us the final result for our differential equation, the homogeneous part of our differential equation. I hope you got my point. Now depending upon the type or the result of this quadratic equation, the solution of homogeneous equation may vary. Let us discuss about that. Okay. Now the first type is that, the type meaning the type of results or roots giving out from this quadratic equation. The first case is that, case 1. The roots of this quadratic equation are real and distinct. Real and distinct. In that case, our result, that is our solution of our homogeneous part, that is our complementary function, is given by, say if the roots are m1 and m2, then the complementary function is given by c1 e raised to m1x plus c2 e raised to m2x. Let us discuss a problem, an example, then we will get a much more idea about this solution part. So the question is that, solve the differential equation d square y by dx square minus 8 into dy by dx plus 5y equal to 0. This is itself a homogeneous differential equation because in the right hand side we can see 0. First form the auxiliary equation. You can form the operator form equation, that is d square minus 8d plus 5 operating on y is equal to 0. Now convert it into auxiliary equation, that is m square minus 8m plus 5 equal to 0. We can factorize this as, this is 8, so we can use 4 and so this is given by, I think this is 15, not 5. This is 15. Okay. Okay. Now we can use 5 and 3 as factors, that is m minus 5 into m minus 3 is equal to 0, or m1 is equal to 5, m2 equal to 3. Now we can give the solution as complementary function is given by c1, the constant of integration, c1 into e raised to 5x plus c2 e raised to 3x. Now in this way we can find the complementary function of any differential equation, any homogeneous differential equations whose roots of their auxiliary equation are distinct and real. Okay. Now let us move on to the second type depending upon the root, that is in the second case, case 2, roots are real and same, that is repeating roots. So in this case, suppose that root is m, then the complementary function is given by c1 plus c2x the whole into e raised to mx. Keep in mind that the second constant terms involves an x term. Okay, this is not c1 plus c2 into e raised to mx, but it is c1 plus c2x the whole into e raised to mx. Now let us check an example. Solve the differential equation d square y by dx square minus 6 into dy by dx plus 9y equal to 0. I am writing the auxiliary equation directly from this differential equation as this is m square minus 6m plus 9 equal to 0. This is actually m minus 3 the whole square, isn't it, equal to 0, or m is equal to 3. This is repeated roots. In this case, the complementary function is given by c1 plus c2x into e raised to mx. The value of m is 3, that is e raised to 3x. This is the second kind of result obtained by the repeated roots. Now in case 3, we may encounter not only real roots but also complex roots. Suppose the roots are in the form m plus or minus is equal to, that is m1 or m2, you can call it whatever it is. If it is in the form alpha plus or minus I beta, then the complementary function is given by e raised to alpha x into c1 cos beta x plus c2 sin beta x. This will be the complementary function if the roots are complex. Okay, where alpha is the real part of the roots and beta is the imaginary part of the roots. I hope you got the idea. Okay, now we can move on to an example. Okay, let us solve a problem involving this kind of roots. Solve the differential equation d square y by dx square plus mu square y is equal to 0, where mu is a constant. Now we can form the auxiliary equation as m square plus mu square is equal to 0, m square is equal to minus mu square, or m is equal to plus or minus iota mu. So our roots are complex, but this does not have any real part. This is a pure complex root. So we can write the complementary function as complementary function is equal to e raised to alpha. The value of alpha is 0. So we can write as e raised to 0 into c1 cos beta is mu x plus c2 sin mu x. E raised to 0 is 1. So we can write it as c1 cos mu x plus c2 sin mu x. So this will be the answer for these kind of complementary functions. Okay, I hope you understand the types of roots and the results, the complementary functions obtained from these types. Okay, if we want the most general solution of a second order differential equation, we have to go to non-homogeneous linear differential equation. So in the earlier session, we just discussed about the homogeneous type in which the right hand side of the differential equation is 0. Instead of this, if we have a function of x in the right hand side, then that equation will become a non-homogeneous. Now in this case, we want not only the complementary function but also the particular integral to get the complete solution of the differential equation. In order to get the complementary function, we just want to equate the r of x equal to 0, then find the auxiliary equation, then find the roots of the auxiliary equation and apply the results from the previous session. But for the particular integral, it will depend upon the type of function, that is r of x. So, depending upon the type of r of x, the particular integral may vary. So, now we can consider the first kind of particular integral, that is the first kind of r of x itself. If r of x, the case 1 is that, case 1, if r of x is some exponential function, that is r of x is equal to e raised to x, then how we can find this equation, the solution of the particular integral of this equation. In this case, the result is given by, that is the particular integral is evaluated by 1 by f of d into e raised to x will become 1 by f of a into e raised to x. Do not get confused. You may have some doubts at what do you mean by f of d. We wrote our differential equation as, one second, f of d. We wrote our differential equation as d square y by dx square plus p into dy by dx plus q into y equal to r of x, isn't it? Then this part will involve the homogeneous part. So, if we rewrite it in operator form, what will be the result? Nothing but d square plus p into d plus q operating on y equal to 0. This term is called the f of d, or the function in terms of the differential operator. So, in order to solve the non-homogeneous equation of the type e raised to ax in the RHS, we have to do this term, we have to apply this term to the denominator and then multiply it with the given e raised to ax. We can have an example so that you will get a much more idea about this kind of solutions. Let us solve the differential equation d square y by dx square plus 6 into dy by dx plus 9y equal to 5 e raised to 3x. So, the general solution of this differential equation will involve, that is general solution is equal to complementary function plus particular integral. In order to have the complementary function, we have to write the homogeneous part. I am just writing the auxiliary equation as this is m square plus 6m plus 9. Solving this, we will get m plus 3 the whole square is equal to 0. So, m is equal to plus or minus 3, m is equal to minus 3 minus 3. Therefore, our complementary function is nothing but c1 plus c2x into e raised to minus 3x. In order to solve the particular integral part, we have to write the function with respect to the differential operator. Here the function is nothing but d square plus 6d plus 9. This is f of d, just from the auxiliary equation. So, to solve this, we have to write 1 by f of d into, in the right hand side there are two terms, that is product of two terms, 5 into e raised to 3x. Keep in mind that in whatever case a coefficient, that is a constant coefficient, is multiplied with the function in the right hand side, you can take that to the result. So, we can take the 5 out of this and take it in the leftmost side of this expression, that is 5 into this f of d is nothing but 1 by d square plus 6d plus 9 into e raised to 3x. The evaluation of this result or this expression is given by, we have to substitute the a value, that is here it is 3 in terms of d, or instead of d we have to substitute 3. That is, this is given by 5 into 1 by 3 square plus 6 into 3 plus 9, which is equal to 5 by into e raised to 3x. That is 5 into e raised to 3x divided by, this is 9, 9, 9, 18, 18, 18, 36. This will be the value of particular integral. So, the general solution is given by complementary function, that is c1 plus c2x into e raised to minus 3x plus particular integral is given by 5 e raised to 3x divided by 36. This will be the final expression for this kind of differential equation. I hope you got the result. Okay. Now we can move on to the second type of R of x. Okay. The second type of R of x, case 2. Here R of x can be of the form, one second. Here R of x can be of the form of a polynomial, that is, it is having a power of x raised to n. In this case, the particular integral is given by, the standard form of particular integral is given by f of d the whole raised to minus 1 into x raised to. This is just the 1 by f of d term itself into x raised to n. We are just taking this to the numerator and expanding it. We know the binomial expansion of this term, because it is a function of d and it is just like a polynomial in d, we can expand it and we can operate it to the x raised to n. Then we can operate it and we will get the result. Keep in mind that if an operator d is operating in a function f of x, what will be the physical meaning of this or the mathematical meaning? This is just the first order differential, that is, if d is operating on x square, this means that this is 2x. Then what will be 1 by d operating on x? If d is the differential operator, then 1 by d is nothing but the integral operator. Keep this in mind. We will have the applications. This is nothing but the integral operator. So, for an example, if we have 1 by d into x, this is not multiplication, this is actually an operation. We are operating x with this operator, where this 1 by d is integral. So, this is nothing but integral x dx, which is equal to x square by 2. Keep this in mind. Now, we can have an example. So, solve the differential equation d square y by dx square plus a square y equal to a square r by p into L minus x. Here a is a constant, r is a constant, p is a constant and L is a constant. A, r, p and L are constants. So, similar to the previous problems, we can find the complementary function as complementary function is given by m square plus a square is equal to 0, that is m is equal to plus or minus ia, and complementary function is given by, this is complex root. So, e raised to 0 is 1, we will get c1 cos ax plus c2 sin ax. Now, for the particular integral, r of x is given by a square r by p into L minus x. Here x is the only variable and f of d is given by, comparing with the auxiliary equation, f of d is given by d square plus a square. So, we can write 1 by f of d into x raised to n is equal to, this is nothing but the right hand side. So, we will get 1 by f of d is nothing but d square plus a square into, this is not multiplication, this is operation, operating on the right hand side, that is a square r by p into L minus x. Now, we want to take this to the numerator, but before directly converting this into the numerator, we can take a square common. It will make our steps much more easier. So, we can take a square common from the denominator and we will get 1 by a square into d square by a square plus 1, isn't it, into a square r by p into L minus x. We can cancel these a squares and we will get 1 by 1 plus d square by a square operating on r by p into L minus x. Okay. Now, we can take this to the numerator, that is 1 plus d square by a square the whole raised to minus 1 into r by p into L minus x. This is 1 plus x the whole raised to minus 1. We can expand it 1 plus x square. This can be expanded and we will get the result as 1 minus x, that is 1 minus d square by a square operating on r by p into L minus x. This result is obtained from the binomial expansion, that is 1 plus x the whole raised to minus 1 is equal to 1 minus, approximately equal to 1 minus x. You will get other terms also, but you do not need that because here it is the d square term that is involving. D square is d square x by dx square. Here we have only the first power of x. So, we do not need the higher power of derivatives. That is why we are approximating it to 1 minus x form, that is 1 minus d square by a square form. Now, we can operate these two terms independently. First 1 into this term and second d square by a square into this term. But we already know that here x is the only variable, and if we operate or if we differentiate x twice, it will become 0. Then this term will become 0. So, the first term, that is 1 into this term, is the only term that is existing, which is given by r by p into L minus x. So, the final solution is given by, general solution is equal to, or y is equal to c1 cos ax plus c2 sin ax plus r by p into L minus x. I think every one of you got my point. Now, moving on to the next type, that is case 3. R of x is equal to cos ax or sin ax, that is trigonometric functions. In this case also, we have to find the particular integral. Here particular integral is given by 1 by f of d into sin ax or cos ax, which is equal to, here there is a difference. Here we are concerned about not f of d but f of d square. That is, simply this means that in these kind of r of x's, that is these kind of non-homogeneous equations which involves the right hand side term is only sin ax or cos ax, we have to find the equation, or our homogeneous equation should contain only even powers of the d terms, that is d square, d raised to 4, etc. So, since we are dealing with second order differential equations, we will encounter only d square terms. So, be careful that we should substitute for d square and the result is given by 1 by f of minus a square into sin ax or cos ax, whichever is given. So, keep in mind that we are not substituting d is equal to minus a. No, this is not the case. we are substituting d square is equal to not minus a the whole square but minus a square. You will get an idea when we do a problem. We can do a problem right now. I think that's the best way. So solve the equation, solve d square plus 4 operating on y is equal to cos 2x. Here we are having f of d square is equal to d square plus 4. We can call it as f of d also, but while substituting we should substitute for d square only. We should not substitute for d. Okay. Now the particular integral is given by, we know about the complementary function. I am not giving out the complementary function, just want to find the particular integral of this term. Okay. Particular integral is given by 1 by d square plus 4 into, here the function is cos 2x. Okay. So substituting this we will get 1 by 2 square can be, or d square can be substituted by, here a is equal to 2, therefore we should substitute minus a square, that is minus 4 plus 4 into cos 2x. Here it will become 0 in the denominator, which is not defined. So this result cannot be taken into account. In these cases where the denominator becomes what we say undefined or undetermined or cannot be determined, we should have another formula. This is the same case for even for polynomials, or not exactly polynomial. This will be encountered mostly in either e raised to x, r of x is equal to e raised to x, or this sin ax or cos ax terms. This is the most common way we will encounter this denominator becomes 0. Okay. Now for this case, keep in mind that if we encounter the same expression in e raised to x, for r of x is equal to e raised to ax, we know that the particular integral is given by 1 by f of d into e raised to x, which is given by 1 by f of a into e raised to x. If f of a equal to 0, then this term becomes infinite, that is not defined, because it is 0 in the denominator. In this case, the particular integral is given, that is for this is simply for f of a not equal to 0, and if f of a equal to 0, particular integral is given by x into 1 by f dash of a into e raised to x, that is we have to take the derivative of f of d with respect to d, that is if we have f of d is equal to d square plus 2d plus 1, and if we substitute some value and this becomes 0, that is f of a equal to 0, then we should substitute f dash of d equal to a, that is 2d plus 2 at d is equal to 2, or d is equal to a, sorry, d equal to a. This is the substitution, and we have to multiply x before this substitution, and then the rest is the just like the earlier steps. Trigonometric functions, just like we encountered in our problem, if f of minus a square is equal to 0, then here also we have some rearrangements. Say here we have to substitute it as, we know that for trigonometric functions the particular integral is given by 1 by f of d square cos ax, so here it is cos 2x, which is equal to f of 1 by f of minus 2 square cos 2x, which is equal to 1 by minus 4 plus 4 into cos 2x, this form. Since the denominator equal to 0, that is f of minus a square is equal to 0, in this particular case only the particular integral is given by x into 1 by f dash of d into cos ax or sin ax. Keep in mind that we are not substituting the value of a or a square in this particular expression. That is, for f of minus a square is equal to 0, that is the denominator becomes 0, then we have to take the derivative just like the function e raised to ax. We encountered it in the earlier problem. But instead of substituting the value of a, we have to take another step, or we have to do another mathematical operation, that is integration. So, in the very example we were discussing about, here f of d square is equal to d square plus 4. Therefore, f dash of d, this can either be taken as f of d or f of d square. Therefore, f dash of d is given by 2d. Now we have to find the particular integral as x into 1 by f dash of d, that is 1 by 2d, into our function, that is cos 2x. Now this 1 by 2 can be taken out and x also can be taken out, that is x by 2 into, this is nothing but 1 by d operating on cos 2x. We have already discussed that 1 by d is nothing but the integration. So x by 2 into integral cos 2x dx, which is equal to x by 2 into integral of cos 2x is sin 2x by 2, which is equal to x sin 2x by 4. So in this case where f of minus a square is equal to 0, the particular integral of trigonometric functions, that is pi is equal to x into 1 by f dash of d into whatever the trigonometric functions there, cos ax or sin ax. But keep in mind that for this case, that is for f of minus a square is equal to 0, the denominator becomes 0, and for this case we will not substitute the value of a, that is a constant in the RHS. Instead, we should integrate our expression and then find our particular integral. I hope everybody got the idea to solve this kind of equations. Now for the final type of equation, that is case 4, we are having some shifting function or some combination of functions, that is r of x is equal to e raised to ax into phi x. This phi can either be a polynomial or be a trigonometric function or whatever function of x it may be. For example, if we consider a problem, that is solve the differential equation, it is expressed in differential operator form, that is d square minus 4d plus 4 operating on y equal to x cube e raised to 2x. So it is clearly, we can see that here in the right hand side there are two functions, that is product of two functions. There is a polynomial and an exponential term. In these cases, the particular integral is given as the shifting property of the exponential function. That is, in this case, the result is given by e raised to ax. That is, in this case, the particular integral is nothing but 1 by f of d into e raised to ax into phi of x. This is the particular integral we are interested with. Its result is given by this e raised to ax term come in front, but it will make this f of d a shift, that is it will be shifted as 1 by f of d plus a into the same function phi of x. I hope you got my point. So in this case, for example, this particular case, we can find the complementary function as well as particular integral. The complementary function is given by, this can be easily converted into auxiliary equation as m square minus 4m plus 4 equal to 0, which will result in m minus 2 the whole square equal to 0, or m is equal to 2. Therefore, complementary function is nothing but c1 plus c2x into e raised to 2x. Now for the particular integral part, we have to consider this property we are discussing about. That is, for particular integral, it is given by e raised to 2x divided by, we are directly substituting the value of the shifted value, that is d, here the function is given by d square minus 4d plus 4. We are substituting, instead of d we are substituting d plus 2. So it is given by d plus 2 the whole square minus 4 into d plus 2 plus 4 into the function is given by x cube, which is equal to e raised to 2x into x cube by, this is d square plus 4d plus 4 minus 4d minus 8 plus 4. So this is plus 4 plus 4 minus 8 plus 4d minus 4d. So we will get e raised to 2x into 1 by d square operating on x cube. Here also we have to integrate, but instead of once we have to integrate twice, because here it is 1 by d square. So e raised to 2x into integral of, first integral result will be given as x raised to 4 by 4 dx, which is further integrated into e raised to 2x into x raised to 5 by 20. So finally we will get the total expression or the final expression as y is equal to complementary function plus particular integral, which is given by c1 plus c2x into e raised to 2x plus e raised to 2x into x raised to 5 by 20. So this is the final result. So I hope everybody of you got the point to solve the different types of second order differential equations. So I think this is all about the second order differential equations of the linear form. Now in the next class we will try to solve another special type of differential equation known as the Cauchy-Euler type of differential equation, and also we will discuss the previous year questions which were asked in CSIR NET, GATE, TAFR, etc. So till then, take care, goodbye.